All right, so we're going to be talking about Learning Objective 5-4, which is to plan and conduct a qualitative investigation to determine what factors affect the strength of a magnetic field produced by a current carrying wire. Obviously, we're going to be doing a lab on this because it does say plan and conduct a investigation, but I want to really focus in this section on the other part of that and give you just a little bit of the background. We're talking about a magnetic field, and the magnetic field being produced by a current carrying wire. So essentially what we're talking about here is an electromagnet. This was a really huge discovery, and it might seem really simple, but this discovery created the world we live in. All of our electronic systems, all of our electronic communication, the internet, Wi-Fi, cell phones, all of it is because one day somebody was messing around with a little, piece of wire right here. Here it is, a wire, and they ran an electric current through that wire. And when they did that, they noticed that it actually would turn a compass. So like they had all these little compasses here, sorry, turned that one the wrong way. They had all these compasses. They were all pointing north just like that. And they found that when they ran an electric current through that wire, it would actually make all of those little compass needles kind of turn just a little bit like this. And they didn't all turn the same direction. Okay, like this one's going to turn back this way. This one's going to turn, oops, that looked weird. This one's going to turn this way. And so what this does is it creates something called a circular magnetic field. Okay. A field is really this sort of complicated mathematical idea, but the whole idea of a field is that extending away from this wire in every direction, there was a certain amount of magnetism, and that magnetism had a strength and a direction. In other words, at every single point of space, there was a vector. Do you remember this word? Vector, a unit with a magnitude, which is an amount, and a direction. And that the vector, the magnitude and direction of that magnetic force, could be represented with these lines, which show the direction that a compass would point if you placed it right there. So you notice that all these compasses point in sort of a circle. So the way we draw the magnetic field, let me make it a little bit bigger. The way we draw the magnetic field is as sort of a circle around the wire. And then you could draw another circle like way out here. And all these circles represent the magnetic field all around that wire. Now, that was step one, noticing that when you run an electric current through a wire, it creates this magnetic field. But step two was then realizing that if you took the wire and you wound it into a circle, you would take like the magnetic field from each piece of the wire and you would compress it together. So now the magnetic field would go through the middle of that loop, and essentially in the middle of the loop it would be really tightly compacted. I don't like the way I'm drawing this right now. Sorry. And so right here you have this very strong magnetic field when you do that. And essentially this is how we make a an electromagnet, is we take a wire and we run a current through it, and then we really coil that wire up. Okay, and this is so useful, this idea of a coiled wire to make an electromagnet, that it actually has a special name. A looped wire that we're going to run a current through is called a solenoid. And we use solenoids in all kinds of devices all around. All right. And then another refinement that we discovered was that if you added what we call an iron core, which is just a piece of iron, or steel has a lot of iron in it, that can kind of work too, but iron is best, in the center of the solenoid, in this case I've got a nail in the middle of the solenoid, that's going to increase the strength of the electromagnet even more. The reason for that is that essentially inside of the iron, it's like you have all these little magnets. But naturally occurring iron kind of has these magnets like lined up sort of randomly. And so the iron itself doesn't actually have a magnetic field, because like all these little magnetic fields from all these magnets, they sort of cancel each other because they're all pointing random different directions. But if you put these magnets inside, or if you put this piece of iron inside of an electromagnet, the strength of the current from the electromagnet the strength of that current causes all of the little magnets inside the wire to line up, just like the compass needles would, around the wire. And so now these little tiny magnets inside the iron add their magnetic fields to the magnetic field of the electromagnet. And so the nail becomes magnetized. If you take it out, it usually is magnetic all on its own after you've done this. And so you get that regular magnet, what we call a permanent magnet, added to the electromagnet. All right. So as far as, that's kind of how an electromagnet works. As far as what factors change the strength of the magnetic field, that's up to you to figure out. And so we're going to do a lab on this, and I want you guys to reflect on what the factors are, and you're going to come back here and actually add to your notes what we discovered.